we will introduce spontaneous symmetry breaking in the context of global gauge transformation. We consider a Lagrangian for a complex scalar field. The reason why we use a complex scalar field instead of a real scalar field is that in order to consider gauge transformation, we need to change the phase of the field, and therefore it has to be a complex number. We included a phi-4 term in the Lagrangian with a positive lambda, which will ensure that we will always have a ground state for our theory. So far, we always considered the constant mu squared in front of the quadratic term to be positive, and that gives us a mass term for our theory. But now we will consider the case where mu squared is negative. In that case, the potential associated with this Lagrangian has a minimum which is not for the field equal to 0. In that case, the vacuum of the theory, which corresponds to the minimum of the potential, is not 0. So we see that the minimum is obtained in the bottom of this potential, which has a continuous set of possible values for the field for which the potential will be minimum. So if we choose one vacuum in this minimum, and we apply the gauge transformation to this vacuum, we see that we end up in a different state, but still in a vacuum. So the vacuum itself is not invariant under gauge transformation. Nevertheless, we see that the Lagrangian itself is invariant under gauge transformation. This situation, in which the Lagrangian is unchanged under transformation but not the vacuum, is called a spontaneous symmetry breaking. This is by opposition to an explicit symmetry breaking, in which case the Lagrangian itself will not be symmetric. We now search for an expression for the vacuum by requiring the derivative of the potential to be 0. An obvious solution to this equation is for phi naught equal to 0, but that corresponds to a local maximum, not to the vacuum. In the case of spontaneous symmetry breaking, we have phi 0 not equal to 0. Notice that mu squared is negative, therefore this is a square root of a positive number. And we introduced nu for later convenience. We now would like to investigate the different possible excitation modes of the field. We see that starting from a given vacuum, we have two possible evolutions. We could move along the bottom of the valley, in which case that does not cost any energy, and we could also move perpendicular to the bottom of the valley, in which case we are climbing the wall, and that will cost energy. The first one is expected to correspond to a massless excitation mode, while the second one will correspond to a positive mass. Indeed, if we had mu square positive, that will give us a quadratic potential and corresponding to a mass term in the Lagrangian. But now that mu squared is negative, we don't have a quadratic potential positively defined near the phi equals 0, which therefore does not correspond to a mass term. However, we recognize such a quadratic potential locally around the vacuum if we go in the direction where we climb the wall. So by calculating the curvature of the potential around the vacuum when we climb the wall, we should be able to extract a mass term. However, for rolling along the gutter, because the potential is flat in this direction, the mass should be 0. So let's investigate small fluctuation of the field around its vacuum. We can choose any point along this circle, and therefore let's just choose it along the real axis for convenience. So we consider small fluctuations along the real axis and along the imaginary axis around phi naught. The Lagrangian now becomes few comments are in order before going further. First, a constant term like this one is irrelevant in the Lagrangian. Terms that are linear in the field are also irrelevant, as we saw earlier when we introduced the first Lagrangian for scalar field. And that's because we can always redefine the field up to a constant and get rid of this linear. So by choosing the origin of eta to be around phi naught instead of the origin for phi equals 0, we can easily get rid of this term. Finally, we only consider small variations around phi naught, so we can neglect term in epsilon 3, eta 3, eta squared epsilon, etc. As a result, we can separate the Lagrangian in two terms, one which only depends on eta and one which only depends on epsilon. So let's first look at the eta term. And for the last term, we have two contributions in eta squared, one which comes from the square of this term, and one which comes from the product of this term times this one. We now use our definition for nu. Combining these two terms, we get, remember that mu squared is negative. Therefore, we can rewrite this term as a standard mass term with a positive mass for the field eta. We can now take the same expansion for epsilon. As expected, the terms in epsilon squared cancel, and we are therefore left with a massless field epsilon. This mode is called the Goldstone mode, and its excitations are called the Goldstone bosons. This is a generic feature of spontaneous symmetry breaking. We usually have two modes, one which has a finite mass and one which is a Goldstone mode which is massless. Note also that we started with only one field, phi, and we end up with two fields, eta and epsilon. And that's because phi is complex, so it has a real and an imaginary part, while both epsilon and eta are real fields. So we kept the same number of degrees of freedom. So this is an example of spontaneous symmetry breaking applied to the U1 gauge transformation. There are other examples of spontaneous symmetry breaking. We will see another one in the case of the chiral symmetry. And then we will generalize what we did for the global gauge transformation to the case of local gauge transformation, and that's when we will see the Higgs mechanism appearing.